Let's try to solve some problems. This may help you identify what aspects from our previous videos that contained a fair amount of calculus, what aspects do you need to understand, what aspects do you really need to practice and incorporate in your understanding. So in this case, we are given a reaction in which the cyclobutane decomposes into two molecules of ethylene. Okay, it's telling us that the rate constant is 87 seconds to the minus 1, which is a pretty fast reaction. Now, and this is something that you have to be able to identify. When you're given the units of the rate constant, remember from previous videos that this is already telling you the order of the reaction. So from these units, the reaction can only be a first order reaction. Therefore, we already know what equations we're going to pick to find the concentrations as a function of time. So when we're being asked what the concentration is after 0.010 seconds, we can just apply the first order reaction in which the initial concentration is 2 molar and the exponent of negative 87 seconds to the minus 1 times 0.01 second. Notice that the time has to be always the same unit as the unit of the rate constant. Whatever it's on the exponent, the units always have to cancel out. An exponential cannot have units in the exponent. This number will give you the concentration when the time is 0.01 seconds. Okay, one just needs to plug in numbers. And this will be in molarity, the same units as the initial concentration. Now, the question is, what fraction of the initial reactant has decomposed in this time? Notice what this gives you is what is left. Okay, so if one computes this, and one just needs to negative KT. Okay, and KT is 7.01. This will give you the fraction, right? A fraction of 1 of what is left. However, we're being asked of what fraction has already gone. What fraction is already gone? This would be 1 minus what is left, or if you will, 1 minus 87 times 0.01 seconds. This is the solution, because if you apply just this equation, this fraction tells you how much is left of the initial concentration. 1 minus that, how much that is left, that is a fraction of what has already gone. Let's practice some more. Another decomposition. Notice that typically decompositions, there's only one here, so typically that's a first order reaction. In this case, it's telling us it's first order, which is redundant because they were also telling us the units of the rate constant, so careful. We do not necessarily need to tell you both, either the units of the rate constant or the rate, or telling you that it's a first order reaction. It's asking first for what is the half-life of the reaction. The good news is that even though we do not have the initial concentration, the half-life for first order is just this equation and does not depend on the initial concentration. This will be like a logarithm of 2, 9.2 seconds to the minus 1. This result will be in seconds. This will give you the half-life of this reaction. For B, it tells you how long does it take for the concentration of cyclopropane to reach 1/4 of the initial. In other words, at what time your initial concentration is 1/4 of the initial. Okay, so if we take this condition and we apply it to the general formula, one just needs to substitute here. This is 0, 4, this is 0, KT. Notice that the initial concentration disappears. So I have 1/4 equal negative KT, logarithm of 1/4 is minus KT, or if you will, the time is 1/4 divided by minus k. Notice that the logarithm of something smaller than 1 will be negative, therefore the negative will be cancelling with this negative, and make sure that your time is positive. Right? Hopefully that makes some sense. It's just through practice that one realizes how important some aspects of each of these equations are.